Input and output. Perfect. We're good to go. So the domain is the input values. Now, pre-calc students, in chapter 3 of your book, it introduces you guys to functions. Again, if you are in pre-calc, please know that chapter 2 of the REA book is fair game for your first quiz, okay? Anything there is fair. So let me know if you have any questions from that. Chapter 3, it introduces you to domain and range again. And you guys remember today I mentioned the name Leonard Euler. You guys remember that today in class, right? In the chapel. And this is one of the most famous notations we use for functions, and that comes from Leonard Euler, okay? So f of x is equal to, and let's use an example here. Yikes, that's not funny, but we'll use the example in a second. Let's start with this example. This is called a linear function, and then we'll use the pre-calc example. What it means is that you have x values and you have y values. You get to select the x values you want. That's completely fine. This is explained in 2.1 of Tyler Wallace, which comes right after chapter 1 of Tyler Wallace, which is equations, right? And what it means is if f of x is equal to x plus 2, is the same thing as y is equal to x plus 2. So you put in a value like -2, you plug in -2 everywhere you see x, right? So -2 plus 2, you get 0. You go on to the next number. You plug in -1. What's -1 plus 2? 1. Okay. We put in 0. We put 0 plus 2 is 2. We put in 1, and we put in 2. Okay. So we picked values that are called input values or domain values, and we get outputs. Okay. So -2, -1, 0, 1, 2. You could pick any numbers you want. So you have 3 and you have 4. Then you go to your graph, and on your graph, wherever -2 is, this is -2, -1, 0, 1, 2, 3. So -2 was 0 for y, meaning that that's the point. -1 is 1, 0 is 2, 1 is 3, and 2 is 4. Bless you. Okay, so then we connect the lines and everybody's happy. We just grabbed a linear function, right? This topic is going to come up over and over and over again. You do it in Algebra 1, Algebra 2, Geometry, Pre-Calc, and Calc. We're just going to do it well once and keep it on file. So that's a linear function. In the Pre-Calc book, they actually give you a 4th degree function, and that's what we're going to try and do as a class. So the principle at work is that there's an input and there's an output. There's a domain and there's a range. There's independent variables and dependent variables. That's what the difference is between domain and range. Now we're going to pull it over here. Those of you who are doing Tyler Wallace, or if you want to work on more linear functions, quadratic, that's fine. But for the pre-calc students, in your notes, so especially those in pre-calc, you need to have 3 points. And here is the function. Okay. So they've given us that function. Looks a little scary, first of all. And they want you to find the domain and the range of this function. And what I would encourage you to do is recognize this is called a polynomial function. And if you've never seen this one before, don't worry. This is called a polynomial function. And the main thing they want you to describe is the domain and the range of this function. Now, I should probably have my computer connected ready next time so I can show you that graph. But the good news is that we don't have to actually plug in all the values. However, I'll do just 2 points. Just 2 points, okay? So wherever you saw x here, you plugged in this value to replace that x. So let's come over here, and if we're trying to make a table of values, we would do this. We have x and we have y. The only points that I would be very interested in using would be let's use -1, and let's use 0. Okay, just 2 points. So then what you need to do is you take this and you bring it over here. X to the 4th minus 4x cubed plus 17 over 4x squared. And actually, if you guys don't mind, I'm going to use -4. That's going to be better. Minus x minus 5. You could choose anything here. Everybody get that? You could choose any value here. So then you take this -4 and you plug it in place of x. And then you take it again and you plug it in place of x. And then you take it again and you plug it in place of x. The point of this exercise is to show you how you input the values, no matter what the equation is. It's about how do I input values, right? And here I'll put 0 to the 4th power minus 4 times 0 to the 3rd power plus 17 over 4 times 0 to the 2nd power. I hope you're seeing the pattern of what we're trying to do, right? We're just substituting the value in, and using a table of values, we're able to find the graph of this function. So I need more room, so I just brought down that x squared, that's -4, minus -4 minus 5. And then over here, it's going to be minus, 0 minus 5. Okay, the point of the exercise, again, is there's an input and there's an output. So can somebody tell me the output over here and the output over here? What's the value when you simplify? For the algebra students, don't worry. Pre-calc students will help us give us the output. So 0 is -5. And how did you get that, Courage? Very good. 0 raised to any power, even if it's a billion, is 0. Everybody get that? So we inputted the values, or we put the values for 0, and the only thing that will be left is -5. Yes, Gideon.
What about the infinite power? That's still 0.
Let's just say I was not thinking I would be raising 0 to infinity today, so let's talk about it on Monday. We could talk about 0 to the infinity power.
My uncle has told me a little bit about calculus, and
Yeah, but 0 to the infinite power, yeah, you're getting into some interesting domain. I would just leave 0 alone, not raise it to an infinite number. But yes, you were going to say? Oh, okay. Oh, do you know the answer to 0 to the infinite power? I actually haven't played with it in a while, so I have to get back to you guys soon.
6 answers.
To which one?
0 to the infinite power.
I don't know the answer to it off the top of my head. No, I haven't played with it. I apologize. So, but given the graph of this function, when you plug in 0, you get that. If we're doing it for a linear function, which I'm going to put back here, so everybody sees the types of functions. They are linear, quadratic, rational, radical, and trigonometric, right? I actually have something for you guys. I'll see if I have it handy. But I actually have a graph, a document that shows you all the types of graphs of all the types of functions so that you guys have it as a resource. Remind me to get that to you guys later. I printed it out, and I just need to pull it up for everybody, okay? I printed it out and left it here. Okay, so let me clean the types of functions. So linear functions, those who are doing my open math, so Caitlin and Gideon, Axel, you guys will go through the linear functions. That's the first one. And then we'll do quadratics, we'll do rational, we'll do radical, we'll do trigonometric. This is pretty much Algebra 1, Algebra 2, and Pre-calculus. All of it is, that's it. It's spending time learning how to graph each one of these. Okay, so let me clean this off. So we know what domain is. We see those input values. We know what range is. Does anybody have the answer for this one, -4, if I plug in -4? Anyone have an answer? Yes. 579. Very good. So 579. I'm not going to double check the work on the spot here, but what we'll realize is that if you were to graph this function, you guys remember how I graphed this and it was just a line? If you were to graph this function, it actually looks something like this. Like it looks like that. Okay, Now you say to yourself, when do I need to know how to graph these kinds of things and how does it apply? A lot of things in the world can be depicted using graphs. So bacteria, for example, there's a graph that will show how many bacteria you will have after 5 years of playing with bacteria in a lab. Does that make sense? Graphs show everything in mathematics. And when you draw these graphs, it is important to understand the input values and the output values. So here's another example. If someone comes to us and says, please graph y is equal to the square root of x minus 2. Okay, somebody says graph that for us. You would go to your table of values and you would say x, y is equal to square root of x minus 2 and y. And you would plug in x values, you would simplify it, and you'll have y values. Okay? So let's do a few spots. First of all, this is going to be tricky. In pre-calc, negative radicals exist. In calculus, they don't. Okay? In calculus, drop the imaginary number discussion. Okay? We don't do that. In pre-calc, we do. Okay? We could just leave it at the entrance for this is the math challenge of the week. So we'll do the one for September 18th, but they can take it early if they want. So thank you. It'll be in the entrance. Thank you so much. So in pre-calc, we talk about imaginary numbers. In calculus, you have to change your mindset and say, nope, drop it. And so what happens is, if I say square root of negative 2, right? Just think about this for a second. What is the square root of 0? Okay, that's not a problem. What is the square root of 4? Okay, what is the square root of negative 4? Okay, but if we're in calculus, what would I say? Not possible. So this is where math is interesting. We teach you how to find the square root of negative numbers, but then there are times where we tell you don't do that. So the reason why that's important is because over here, the x values I choose here, right? Let's say I choose x is 2. That means y would equal the square root of 2 minus 2, which is the square root of 0, which is 0. Everybody's happy. What if I choose 0? That means y is equal to the square root of 0 minus 2, which is the square root of negative 2, which in the real number plane, can't use it. What if I choose 1? That means y is equal to the square root of 1 minus 2, which is the square root of negative 1, can't use it in the real number plane. But what if I choose 4? Well, actually, let's go with 6. Let's say I choose 6. That means y is equal to the square root of 6 minus 2, which is the square root of 4, which is 2. Check. Any number that will make the radical negative will not be included in the domain of the radical. That's kind of what they're trying to say. Does that make sense? Okay, yes?
When would we ever be able to do this? Like for 6, obviously, for 4, but it could also make it 2. Wouldn't we also be able to, on the y-axis?
No, you don't graph on the real number plane. This is like the real number plane. This is what most people use in a general sense every day. Real number plane, like how much is our GDP? It's a real number, right? Generally speaking. But when you get into imaginary numbers, that's a different plane, and that's a different sort of situation.
I just mean like let's say you said, okay, we should go and graph this.
Yep.
And I wanted to graph it when x is 6, right? So I graph when x is 6, and for my y, it would be 2.
Yes.
Right? But couldn't my y also be negative 2?
Oh, no, we would use the positive value of the square root.
When would we ever graph negative 2 on y? We would never ever, in like any other occasion, ever graph negative 2 as a y-axis.
So what Courage is saying is the square root of 4. So 2 times 2 is 4, but negative 2 times negative 2 is also 4. You see what Courage is trying to say? So if we said square root of 4, why couldn't I have written that as negative 2 when it's simplified, right? Because the square root of a number, in one sense, is like you have a positive and negative value of that number. So it can either be that or it can be that. Everybody see what's going on here? He's saying you could have two different answers. And that's a good observation. But in this particular case, how will I address it? I would say that generally speaking, in this particular case, I wanted to say you could try doing the two on the same graph, but I wouldn't do that. I would just use the positive value of it. We'll let you know if you did. Yeah, no worries, we will. Yes? Yes, you may. Oh, okay, no problem. Okay, so the point of this activity here, though, again, everybody follow closely the pattern, is that you choose the input values. Some people think math is all objective and you can never have a choice. Oh, you have a choice. You choose what you want here, and then you substitute it in, and then you get a y value. Now, granted, this got a little messy, but you get a y value. Everybody get that? Okay. We're going to talk about domain and range later in more detail, but I want to pause for a second and actually look at a few examples that will make more sense. Let's evaluate some functions together. So in your notes, go ahead and write evaluating functions. So let's evaluate some functions together. Okay, so the title is Evaluating Functions. Okay? This is what I would probably want to focus on a mini quiz, is evaluating functions. So if you're given f of x is equal to 3x squared plus 2x minus 1. If somebody says that's the function, and they ask you find f of 1, okay? What they're saying is everywhere you see x, change it to 1. So then when you rewrite the question, you basically write 3 plus 2 minus 1. I changed everything that was x to 1. That's what they're asking for. So then in this case, it's 3 plus 2 minus 1. We're doing arithmetic. We're doing third grade math at this point. But in the beginning, you just had to understand that 1 now represents the value of x. Everybody see that? That's what they're trying to show us. What if then, so then what's our final answer here? We just say 4. Okay, and everybody's happy. But then what if they say f of a? Can you guys try that in your notes? What is f of a then? So go ahead and write it down. We'll just look at a couple more examples, and then we'll give you time to practice. So f of a would be, I take a, and where do I put it? Everywhere I see x. Very good. So everywhere I see x, I put in a. What is f of, for lack of a better example, what is f of triangle? It will be 3 triangle squared plus 2 triangle minus 1, right? That's the way it works. Yes? Well, in this case, I use the triangle, but it is delta. In calculus, we call it delta as well. Yes. Very good. So this is just showing you how input values represent something in the original equation. Okay, let's land with a few sketches, and then you guys are dismissed. So, to study and work through practice. So next week, God willing, Algebra 1 students, you guys will be working through graphing. Keep working through graphing. Those who have been doing factoring and rational expressions, just keep going along. That's fine. But we are all going to then find a balance, because again, today's the first day. We only have one math class at this hour. So we'll see how we navigate that together. Okay, some fun stuff with graphing, and then we'll sketch. If f of x plus g of x, let's say f of x is x plus 1, g of x is x squared plus 2. If somebody asks you what is f of x plus g of x, what they're saying is take everything that is called f of x and take everything that is called g of x and add them together. That's what they're saying. So in this case, it would be x plus 1 plus x squared plus 2. So this is x plus 1 plus x squared plus 2, which brings us to this topic called like terms. And what are like terms? The same variable in the same power. This is from pre-algebra. Maybe I should, remember in pre-algebra, you have like terms, but again, the way I teach, I generally will assume that you don't know anything from the past generally. So I'm going to say you didn't know this, and I'll just say x here cannot add with anything because there's no other x. X squared cannot add with anything, but 1 and 2 can add because they're of the same kind. So it's x squared plus x plus 3. Sorry, I was rewriting 1 and 2, but it's 3. Okay. So pre-calculus students, chapter 3 is where you're going to camp out. Make sure you're good to go. Chapter 2 and 3, that's what you need to finish out there. College algebra students, this topic is also in your book from chapter 4. They just give you more examples than they have. And it talks about graphing lines. It talks about definitions and so on. When I said I wanted to end with a sketch, this is the sketch I want to end with. All these functions, like this one I just wrote here, would fall under like a quadratic polynomial type function. That is a radical, right? Everybody remember we've talked about radicals already a little bit in this class. Those who are doing Tyler Wallace, you're going to be doing linear functions like this one. That's linear because it's in the first power, right? There's nothing there. When we just have x plus 2, then it's in the first power. This is in the second power. So these are the sketches for the day. What kind of graph would look like a U? That would be a quadratic. What kind of graph would look like a straight line? Like that? That would be a linear. And then what kind of graph would look like something like that? That would be a radical. And so what I printed, which I'll go grab for you guys, is basically the different types of graphs, and we can be referring to it regularly. So we have linear, which is from chapter 2 of Tyler Wallace. We have quadratic, which is from chapter 9 of Tyler Wallace. We have radical, which is from chapter 8 of Tyler Wallace. And then pre-calc students, you'll be doing trigonometric graphs like sine, cosine, tangent, cotangent, cosecant, secant, and so on and so forth. Okay, so we've talked about domain and range. We've talked about adding functions together. Next week, we'll talk about composition of functions, which is discussed in the college algebra book as well as here. We will also discuss parent functions together. Make sure that you're comfortable with how to graph a function. Just remember the big thing with graphing anything is have input values, put them into the equation, and you get output values, and then you sketch. That's how we deal with these graphs, using a table of values. Are there any questions before you work more on your practice problems and I go around and check on people's work? Yes?
So, for the college algebra, you want us to do like what we've been doing, like just keep going through it?
Just keep going through it. Yep. Because I don't want you to waste time relearning a topic you already know. So when you take your book and you look through the examples and you do the practice there and you're comfortable, move on to the next page. Does that make sense? There's nothing wrong with that. Yes?
What do you want us to do the practice from?
But from your, pre-calc students use pre-calc, college algebra use college algebra, Tyler Wallace use Tyler Wallace.
Do you want us to go from where we are or from the chapter?
Be where you are, but at least make sure you're going into chapter 3 and getting ahead of chapter 3. So, if you have questions from any of the previous chapters, let me know. I'll be available to answer questions. Okay, and then I'll just let you guys work in your groups or in your table, and I'll answer questions as I go around, okay? If you have any questions. So if you have your Tyler Wallace book,